Let's take a look at an expected value example problem. Here's the game. You're going to flip a coin followed by rolling a die. There are three possible outcomes of the game. Number one, if you flip the coin and it's tails, the game is immediately over and you lose $4. You give $4 to the game maker. Number two, if you flip a head, then you get to roll the die. And if you roll a 2, 3, 4, 5, you win $2. Number three, if you flip a head and you roll a 1 or a 6, you win $10. The question is, what is the expected value of the game? As a reminder, the expected value is the average of all of your winnings and losings that you would expect if you played the game a large amount of time. An expected value of 0 means the game is fair for both sides. A negative expected value means the game favors the game maker, and a positive expected value means the game favors you, the game player. Expected value is calculated by multiplying all of the outcomes times their probabilities and then adding up that sum. The three different outcomes that we can have are losing $4, which we would represent by -4, winning $2, represented by +2, and winning $10, represented by a +10. So there's our three outcomes right here, 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 and here. And for each of those, we need to multiply the individual outcome by its specific probability. So in this parentheses right here, we need to calculate the probability that we lose $4. Or in other words, what is the probability that when we flip a coin it's tails? In this case, that's a very easy probability to calculate. We can just do it in our head. It's 1/2. Move on to the second one. What's the probability that we win $2? Well, that's the same as saying the probability that you get heads and a 2, 3, 4, 5. Now, because we have two things going on here, we first identify, are they independent or dependent? In this case, they're independent. So the probability of heads is equal to 1/2. That's easy enough. And the probability of a 2, 3, 4, or 5 is 4 out of 6. That's also easy enough. Do not make the mistake of adding these two numbers. The probability that both this and this occur is the multiplication of these two numbers, which turns out to be 4/12 or simplified 1/3. I'm going to repeat a very similar process for this final probability, which is the probability that we win $10, which happens if we get heads in a 1 or a 6. So the probability that we get heads, we've already established, is 1/2. The probability that we get a 1 or a 6 is 2 out of 6. When we multiply those together, we end up with 1/6 simplified. And then finally, to calculate this expected value, we just need to calculate this sum. So if I go through here, I do this multiplication, I end up with -2. I do this multiplication, I end up with +2/3. And I do this multiplication and I end up with 10/6, which simplifies to 5/3. Simplify further, I get -2 plus 7/3. If I put -2 in terms of thirds, that would be -6/3 plus 7/3, which ends up being a +1/3. The expected value of this game is 1/3, or if we put that in terms of dollars, $0.33 or 33 cents. Because the expected value is positive, the implications are that this is actually a game that is in our favor. But we're not advocating for gambling here. All we're saying by that is if this particular game was played millions and millions and millions of times, each time it was played, the person playing either loses 4, wins 2, or wins 10. But over millions and millions plays of the game, if you were to average all of those winnings and losings together, that average would get closer and closer and closer to 0.33, meaning that the person playing the game is actually making money on average in the long run when they play the game.